Welcome to the next scale model, 1 to 1 billionth. We'll call this the Nano scale model. Nano coming from Greek, meaning dwarf. And this scale model is the first time we can look at atoms up close. This is a scale model of a hydrogen atom, enlarged by 1 billion times. It's one of the smaller atoms. So the ancient Greeks came up with the idea of the atom. Democritus theorized back then that everything around us is made up of tiny building blocks, and you couldn't divide it anymore. And that was really a novel idea because everything at our true scale is unique. Leaves on a tree, or snowflakes, or even grains of sand. There are no two grains of sand in the universe that are the same. And an atom is the same no matter where you find it, here on Earth or in another planet, in the Andromeda galaxy. Ideas like a Lego set where you have relatively few parts, but when you combine them, you get almost an infinity worth of complexity and variety. And it was later in the 1800s that the modern atomic theory came into being. The atom was then put in a chart where, as you've all seen this in school, periodic table of elements. If we look at the same table, but in terms of the size of the atom, we come up with something like this. So the atoms start on the small side with hydrogen. Helium, turns out, is a little bit smaller. And then it kind of grows in size, but then it tapers off until you get to the largest atom, which is cesium. Here's some relative comparisons of atoms. Hydrogen, and then we go to oxygen, carbon, uranium, and the largest atom, which is cesium. Hydrogen makes up 75% of the universe. It was made primarily in the Big Bang. So we could almost say they're the oldest atoms. Oxygen, carbon, all these other ones, they're all made in nucleosynthesis in the stars. So oxygen, which we use for breathing, often combines with two hydrogens to make a water molecule. Carbon is the superstar element. It just combines with almost, with a lot of other things, other molecules, atoms. And it's the basis of DNA too, which we'll talk about. Uranium, this is the heaviest element by atomic weight. So it has the most protons and neutrons in the middle out of all of them. But it's not the largest atom. The electron shells that surround it and that define the diameter of the atom, they're packed in a little more densely. And then we have cesium all the way over here. Cesium being the largest of the atoms. DNA is the genetic code of life, and it consists of a double helix. So it's like, imagine like a ladder that goes up with rungs, and the whole ladder is twisted. And the rungs contain the genetic code of all life. So the width at this scale is about 2 meters wide. Every human cell has about 6 billion base pairs, so these are rungs on this staircase. The twist takes about 3.4 meters to make one twist, right? So this tree in the background, that's about, let's say, it's about a little more than 3 meters, right? So imagine the twist taking that much height. And the rungs on this ladder are 32 centimeters apart. So this is a staircase that at this scale model, I could easily climb it. And if I were to look closely, there would be chains based with a lot of carbon in it. And the carbon makes these long complex chains, of which there are 4 types. And these 4 types, like a computer, like we use zeros and ones, DNA uses 4 different fundamental codes, let's say, when combined in different ways, makes up for a genetic blueprint. In the 1900s, Rutherford did experiments that showed that the protons are all packed very densely in a nucleus. Later, the neutron was discovered, and it lived in the nucleus as well. And that's where most of the mass of the atom is. And the electrons were way out in living in this energy shell. Various shells, and they have rules of how close they can live to each other and what shells they live in. But the outer shell is kind of the defining diameter of an atom. So we're getting into the subatomic particles now. And to look at that in a scale model, we have to go one level deeper to start to see what the nucleus might be, how large it would look like. Right now, at 1 to a billionth, the nucleus is still invisible. We'll see you in the next video.